All right, now that we can calculate internal forces, we are going to look at the graphs that can be made from these forces. Now, we're not going to graph the axial force. We are going to focus on the shear force and the bending moment. And we'll see why, because part of what we're going to do is look at the relationships between the two of them. So let's say I have one. And I guess even before that, no, let's just go to this one. This is a pretty simple piece, but if we were dealing with a frame piece and it had truss pieces attached to it or other frame pieces attached to it, right, there's a lot that could be going on. But in the end, we can boil it down to what's the shear forces and what's the moments, right? We can boil it down into these. So just to say it, let's say I had a piece that was like this. Oh, what just happened there? I had a piece like this, and then it was attached by a truss piece here, and a thing here to the wall, and then there's a roller. And this drawing's looking worse and worse. And then I had another piece that went like this, and then I had another piece that went like this. And I could try and make this fairly complicated if I wanted to, right? And then let's say we had another piece that went like this. And we had a lot going on. And I had another piece that went like this. There we go. Now, if I could solve for this piece, well, then I know here there would be some type of axial force. Switch colors. At this point, there would be some type of axial force. There would be some type of shear force. And I'm not saying it would be easy to find, but that's what there would be. And I go here again, there'd be some type of axial force, there'd be some type of shear force, and then here there'd be same thing, some type of axial force, some type of shear force. So while I wouldn't want to tackle a problem like this because there's a lot going on, once I get to the point that I solve for everything, well then I could say, hey, I've got this piece and it's got an axial force here, it's got an axial force here, it's got a shear force here, it's got a shear force here, and it's got a shear force here. Now I've simplified this complex thing, and all I'm looking at is the shear forces, right? So these things could be done. So this could be a very complicated problem. This could also be a very simple problem, right? This could be a problem where I just have a piece. Wow, that's awful. And it's supported there, and it's supported there, and there's a downward force of 120 newtons there, right? It could be this simple, could be this complicated. In the end, it doesn't really matter for what we're doing, what's the problem that gets us to this. But I have this problem, and I see the external forces. Now, before I make the graph, we have to establish some direction, what's positive, what's negative, so all our graphs look the same. Even if we didn't do this and I'd let you choose, then what we'd have is we have half the class that would have one graph, we have half the class that basically has the upside down or the inverse of that graph is really what it would be. And in the end, it would both work, but we want to make sure that we're all doing it the same way. So we're looking at the external forces. And when on the left side the force is up and the right side the force is down, that's a positive shear. When the left side is down and the right side up, that's a negative shear. Then we're looking at the bending moments. If the external forces are trying to bend it into a smile, that's a positive bend. When the external forces are trying to bend it into a frown, that is a negative bend. So we establish positive and negative. And let's go back and try this problem. So I'm going to make a graph. And I'm going to make a graph of, first we'll deal with the shear force versus distance, right? So these forces versus the distance. And we're going to focus on the external ones, and we are going to establish what the external forces are, and we're going to make a graph of them. So if I go left to right, then, if I go left to right, then what I have is at distance 0, I have 90 newtons. So 90 newtons, and I'm right there. Now, if I keep going, and I'll say let's go every meter. So we're at 2 meters, we're at 3 meters, we're at 4 meters, we're at 5 meters, we're at 6 meters, we're at 7 meters, we're at 8 meters. And they're not broken up too badly. So let's try and plot this every meter. So at 0, it's 90. I go over to another one and I keep looking at my external forces. It's still 90. So 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters, 8 meters. At 1 meter, we're still at 90. At 2 meters, we've got a jump. We have 90 up, we have 120 down, right? So that's 30 down. Well, when the left side is down, that's a negative. So we go down to negative 30 newtons. Right? Even if we do it by half a meter, right, it still would be 90, then 90, then 90, and then here we have a jump, and we have a jump all the way down to negative 30. Now I keep looking, and when I do here, it's 90 up, 120 down, negative 30, negative 30, negative 30, negative 30, negative 30. So let's go all the way to 7 meters, and it's negative 30 all the way, because if I keep adding these two up, it's left side down 120, up 90, works out to be a total of down 30. Then when I get to the 8 meter mark, I have 90 up, 120 down, 30 up. I add all those, it gets to 0. And I expect it to get back to 0. I do. So I get a shape something like this. So if I plot the external forces as I move left, as I move left to right, this is what I get. Now just to say it, what if I moved right to left? What if I started, there we go. What if I started here and I went that way? Well, if I was a half a meter away, it'd be 30 up on the right. Well, if I go back to my shapes, if the force is up on the right, that's a negative shear. So still works out to be negative 30. If I keep going, it's 30 up, 30 up, 30 up, 30 up. Once I get to here, it would be 90 down, but it's down on the right. And when it's down on the right, it's positive. So I would still see the same jump, right? So if I go left to right in this situation, I'm dealing with this because on the left side the force is up and then the left side the force is down, right? So I see the jumps. If I go the other way, I'm seeing the exact same thing. So no matter what side I start from, I'm still getting this. All right, now let's look at the bending moments. Well, if I start here, I have a force of 90 newtons, but I have a lever arm of 0. If I make this my pivot point, there is no lever arm, so I have a moment of that, 0. Let's do it for a meter. Well, I have a force of 90 newtons. I'm a meter away, so I expect this to be a bending moment of 90. So I'm still a meter away, and I have a bending moment of 90. I go to the next one, 2 meters away. I have 90 times 2 is 180. And I have another force, but the lever arm for this is 0. So it's 120 times 0, 0. So at this point, I have a moment of 180 newton meters, 90 times 2. So this was 90 newton meters. This was 180 newton meters. Now let's go at 3. So let's go here. Well, I have 90 times 3, works out to be 270 newton meters. And then I have 120 times 1. So this one's pushing up, and it's 3 away, so it's going to try and bend it this way. Oops, sorry, there we go. Which is a positive. It's trying to bend the left side up, which is a smile. 120 times 1, well, this is pushing down, right? We've lost our down arrow, so this is causing a bend that's this way, a frown. So this is producing a positive bending moment. This is producing a negative bending moment. So that is 120. So they're in opposite directions. So if I combine them, I get 150 newtons. I could do the same thing for here. At 4 meters, it's going to be 90 times 2. It's going to be, I'm sorry, 90 times 4. It is going to be 120 times 2. That's a 4. There we go. I should be able to do this in my head, but 90 times 4 is going to be 360. 360, 240. It's going to work out to be 120 Newton meters. And then I do the next one. I'll do it over here. 90 times 5 and 120 times 3. 450 in one direction. 360 in the other direction. So that works out to be 90 Newton meters. We're starting to see a pattern. I got to 180 here, right? Then I went down by 30. Then I went down by 30. Then I went down by 30. So as I get to 6 meters, I expect to go down by 30 again. Let's just see. So it's going to be 90 times 6 because we're 6 meters from the end, but the 120 is 4 meters away. 90 times 6, 540. 120 times 4, 480. And I combine them. I'm at 60 Newton meters, so it's another drop of 30. Then we'll do 7. And you know what? I'm going to erase my drawing down here because it's just in my way. And we'll do 7 and 8 just so we have them. 90 times 7. 120 times 5. This works out to be 630 in the positive. This turns out to be 600 in the negative. 30 Newton meters, still positive. They're all positive numbers because it's the bottom ones that are all negative. Negative, 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 negative. And then the last one, which is one I do want to see, I have 90 times 8. I have 120 times 6. 90 times 8 is 720. And 120 times 6 is 720. And I have another decrease of 30, which brings me to 0. So if I plot these moments, I'm going down by 30 all the way till I get to 0. So I know this is 0, and I know I'm 80, 150, 120, 90, 60, 30, 0. So I am going to cheat a little bit on these. Let's try that again. There we go. So this is going to be a straight line going up by 90. And then this is going to be a straight line going down by 30. So I get something like this, and I think I'll try to draw and fill them in a little bit. Maybe I won't because it doesn't like it. Come on. I have a straight line going up by 90. I got a straight line going down by 30. So if I look at this, my shear force is 90 newtons. I have an increase of 90 newtons per meter as I move this way. Then as I go, I have a shear force of negative 30 newtons. I have a decrease of 30 newtons per meter as I go. other thing is I really start at 0 and I go up to 90. I go around and I end at 0. Here, I start at 0, and again, I end at 0. These are good things, because if I don't end at 0 for my force, that means this piece is moving up or down. And if my bending moment doesn't go back to 0, then that means this thing is spinning, right? So the fact that they get back to 0 means that all the forces cancel each other out, and it means all the moments cancel each other out. So here are my two graphs. Now, what else do these two graphs tell me? Well, it tells me a couple things. For this one, which is a fairly simple piece, here's the place where if it was going to shear or snap in half, that's where I'd expect it to go, right? On this piece, if it was going to bend, this would probably be the point that it bends around, right? So it's telling me some things, where it's most likely to break, where it's most likely to bend. All right, so let's look at a different one. And we're going to deal with a more complicated situation, but we're not going to solve for the external. I'm going to solve for the external forces, but I'm not going to go through all of that. So if you need to, because it's definitely part of this, right? Make sure that you understand what forces we have. So let's say we have this, it's supported here, it's supported here, and let's say that it is 32 inches long from end to end, and if I go 12 inches, a little more than a third, what I have is I have a distributed load. So we're going to do something a little different. We're going to do a distributed load, and from the end of this beam all the way over to 12 inches, I have a uniformly distributed load, and we're going to say that it is 40 pounds per inch. Then we're going to go another 10 inches. And we're going to say there we have a point force. We are going to say that one is 400 pounds, sorry. So there's my setup. I have a distributed load, 40 pounds per inch from here to here. As we keep moving over, there's more and more force pushing down. And then I have a 400-pound force felt right here, 10 inches away. And just to save you from doing the math, that means from here to here is another 10 inches. All right, so you can do some of this yourself, and if I'm kind of going too fast, you're like, I'm not sure how they got it, go back and look, right? Go back and look. So I have 40 pounds per inch, and this is going for 12 inches. So I could say that this applies a total force of 480 pounds down. And based on my knowledge of centroids, and it's a rectangle, that this 480 pounds is effectively felt 6 inches away from the end. Now this is going to change my shearing graph. It is going to change both of my graphs a little bit, because it really isn't 480 pounds right at this point. But as I'm dealing with over here, mathematically I could say it's there. But as I'm in here, it's going to be slightly different. So I have 480 pounds total down. I have 400 pounds down, so I have 880 pounds up. If I made this my pivot point, I can calculate for the force up here, and that force works out to be 365 pounds. And I know this plus this have to add up to 880. So I know here there is a force, and there is a force of 515 pounds. So when I look at this, I essentially have, ooh, these lines get worse and worse. I essentially have a force here. I have a distributed load with a force effectively located there. I have a force here. I have a force there, right? But then again, this one is all of these downward forces all the way through 12 inches. All right, so let's start. I look at my shearing force, which is where I'm going to start. Now I look at this. I initially have 515 pounds up. And then this is 40 pounds per inch. But if I start here, there are no inches yet. So there is no force due to this distributed load yet. There will be as I start moving left or right. But at this point, I start at 515 pounds. And then I see, as I move to the left, every inch that I move, I go down 40 pounds, or there's an additional 40 pounds down. So here, once I get to here, there's 515 up, but there's 40 down. 515 minus 40 works out to be 475. Then I go here, there's another 40 pounds down. So I take that, 475 minus 40, or 515 minus 80, 435, right? So once I get to this point, 12 inches away, I now have a total of 480 pounds down. 515 minus 480 works out to be 35 pounds. So when I get to, let's kind of mark these off as good as I can. So we're going to say this is 12 inches, and then I go 10, so that makes this 22 inches. I go another 10, that makes this 30 inches. So I know that I start at 515 because it's 515 up, and I know it goes down by 40 until I get to 12 inches away. So in the end, it goes down by a total of 480, right? But it doesn't all happen right here. This is a distributed load, so it's going down by 40 each time, but there's a total force down of 480, which I get to finally when I get to there. So I'm going to get to this point, and this point is 35 pounds. And let's see if I could do it this way. Get this. And it's going to be a straight line because it's going down by 40 each time. I don't know why I can't make fat straight lines, but there it is. So it's going to look like that. And now let's go to the next part. Well, there we go. From here to here, the next 10 inches, I don't have any other changes. So all of this, 515 up, 480 down, works out to be 35, and there's no other forces, so it's 35 up the entire way, right, for the next 10 inches. So I get something that looks like a horizontal line, and that horizontal line stays at 35 because there's no more external forces. Then I have a jump, and I have a jump of 400 pounds down. So 515 up, minus 480 down, minus 400 down. My force is 365 down, or negative 365. So I have a jump, and now it's a jump because that's a total, that's a force felt right at that point. So negative 365 pounds down, and that is a jump. So I'm going to see it go like this. And then I continue, and it doesn't change, doesn't change, doesn't change, doesn't change. It's like at the very end, and there's 365 up, which is good news because that means I am here, and then I see a jump of 365, and I go back up. So I have a graph that looks like this. Diagonal, because it's the downward distributed load, stays the same, and then because there's a force that's essentially a point force, there's a jump, and then there's again a point force, which is the reactive force of the base, goes back up, and this is my graph. Now, if I look at this, as I move this way, this force, right, the first 12 inches, this force is going to be a constant 515, and I'm going to keep increasing my distance, so the moment produced by this is going to go up. As I move over, the forces are increasing, and the distances are increasing for this, right? If I dealt with 6 inches, then I wouldn't have a force of 480. I would have a force of 240, and it would be 3 inches away. If I went here 9 inches, then I would have a force of 40 times 9. That 40 times 9. I would have a force of 360, and it'd be 4.5 away. So as I move this way, this is going up linearly, just like it was with this one, right? But my distributed load is increasing in force and lever arm. right? Both of those things are increasing. So I see this have more and more and more of a drastic effect as I keep going over, where this is going up linearly. So what I would get is I would get something that looks like this. Starts out kind of steep, and then it gradually tapers off, something like that. And then when I get to here, well, the forces don't change, so I effectively have 515 and I have 480. Now I can deal with, 2-point sources because I'm outside of the distributed load. So this downward force isn't going up anymore. It's effectively 480 at this point. And like when I'm here, what I'm saying is I don't really have 480. Some of it's on this side, so I'm not really dealing with that. I'm only dealing with what's on the left side. So I have 515. Let's go ahead and do it. Let's get rid of all this. There we go. So if I go to there, I have 515 times 22 inches. Then I have 480 times, let's see, 16 inches. This would be a positive moment. This would give me a positive moment of 3650, and that would be pound inches. And you know what? Just to do it, I'll change color, but let's pick this point. Let's pick at 12. 12 right here. So for 12, what would I have? I'd have 515 times 12, and I'd have 480 times 6. This one works out to be 6180, and the other one is 480 times 6, 2880. One's positive, one's negative. 3300 pound inches. So I go back to this. This is 3,300 pound inches right there. And then I go another 10, and I go down to 3,300 pounds. Oops, sorry. I don't go down, sorry. I go up. I go up to 3,650. But there it is a straight line. Something like that. And then, when I get to the last part, now if I look at the last part, there we go, come on. Once in a while, this pen just has its own mind. There we go. All right, now if I look at the last part, or what did we do so far? Let's see. We went to 22, so we went to here. We have 400 down, so we went to here. Now, as I start to move this way, I have a 480 down, which is effectively located here. We have a 515 up, which is located at the end. We have 400 down, which is located here, and we have 365. So now I'm going to go to here. Or you know what? Let's pick another spot. So this is 22, this is 32. So let's pick halfway in between 22 and 32, 27. So let's pick 27 inches right there. So it's 515 times 27. Then I have 480. Well, now I need the distance from here to here, which is 27 minus 6, 21. And then I have 400, and that one is 22 to 27, 5 inches, right? So I have 515 times 27, 1, 3, 9, 0, 5. I have 480 times 21. This is going to be negative 10080. And then I have 400 times 5, negative 2000. I add all these up. I still get a positive moment. But it's small, 1825. And then let's change colors here. And let's do this one. So I have 515 times 32. I have 480 times 32 minus 6, 26. I have 400 times 10, 515 times 32. That's going to be a positive moment. 16480 pound inches. This one's going to be a negative moment. 480 times 26 works out to be negative 12480 pound inches. And then 400 times 10 is going to be a negative 4000 pound inches. All of that combines to give us 0. So I know that I'm starting here, and I am going to go down to 0. Like that. And it's going to be a straight line. It's going to cut in half, and it's going to get cut in half. So I get a curve. I get straight. I get straight. Now, last time we made the observation, which is really kind of what we want to do because it's going to make things faster. It was a positive shear force of 90. It was a positive slope of 90 newtons per meter. It was a shear force of negative 30, and the moment went down by 30 going along the bending moment. So this value is the slope of this line. This value is the slope of this line. Or our shear force, when I graph force versus distance, is the slope of my bending moment versus distance. This value is the slope of this line, or the other way around. The slope of this line is this value. Well, looking at this one, I have a positive slope, but it's getting less and less and less. So the slope is getting less steep and less steep. So I have something that is very steep and becoming less and less steep. And then here, I still have a positive value, which means I still have a positive slope, but it's small, but it's constant, straight line. Then down here, I have a negative shear and force. Therefore, I expect to see a negative slope. I expect to see it go down to 0. So this works out well. All right, last problem. I have a beam again, and we are going to say 6 feet away, there's 20 kips down. Another 8 feet away, there's 12 kips down. 10 feet away, there is another support, right? There's support here and at the end. Then there's a distributed load of 1.5 kips per feet, and it's for 8 feet, so 1.5 times 8, 12. There's a total of 12 kips down here, and it's felt 4 feet away from this support, right? So that works out to be 12 kips. Oh, that's awful to see on there, 12 kips down. And again, it's if I'm over here, it's effectively fell at this point 4 feet away from the end, 4 feet away from the support. But when I'm in here, right, I have to understand that it varies by 1.5 every foot because it's a distributed load. Now, with all that said, the reactive forces turn out to be, well, this has to be up, this has to be up, and this one works out to be 18 kips. There's a total of 42 down, so it's got to be 42 up. So if that's 18 kips up, then this one works out to be 26 kips. So there's 44 down, and there's 44 up. I don't know if I said 42 before, but the total down and the total up cancel each other out. We pick up pivot point, everything works again. You can check those if you want, but these work out okay. So now let's look at the graphs. I'm going to go a little fast on these graphs. For the first 6 feet, I'm 18 up, and then I'm going to go 20 down, then I'm going to go 12 down. So from here to here, it's going to be 18 up, then it's going to be minus 2, then it's going to be minus 24, and then it's going to be jump up to, then I'm going to see a jump. Say this again. It's going to be 18. This is going to be minus. This is going to be 18. This is going to be minus 2. This is going to be minus 14. Then I'm going to jump up this one, so it's going to be plus 12, and then it's going to gradually go down. So it's going to look something like this. 18. And then it's 18 plus 20 down, so it's going to be minus 2. That's going to be minus 2 for the next 8 feet, and it's going to drop to minus 14. And then it's going to be at minus 14 from here to here for the next 10 feet. So I'm going to make this minus 14, and this is minus 2. And then it's going to jump up, it's going to jump up 26, so it's going to go plus 12. And then it's going to gradually go down because every foot I go, it's a drop of 1.5 for a total drop of 12, which means it's going to do this. Back to 0. And I know it's got to get back to 0, so getting back to 0 is a good indication that I've done it right. So I'm going to get a pattern that looks like this, which means here, this value is a slope of this. I expect to see a straight line going up. Oop, let's erase that, try that again. Delete. There we go. From this point to this point, I expect to see a straight line going up. And then it's a straight line, but it's going down gradually. It's not nearly as steep as this, because this is a slope of 18. This is a slope of minus 2, so we're going to have something like this. Then I'm going to see a slope of minus 14, and I'm going to tell you it's going to go something like this. And then it's a positive slope that is decreasing, so it's going to do something like this. So just by matching up the slopes, I can do that. But now I can get these points. Now one way I can get the points is keep doing what I was doing up here. I could keep finding these things, right? But I could actually do it differently. This is the slope of this line, or the slope of this line is this value. The other thing that I could say is the area underneath this is the change in this. So I have 18 times 6, 18 times 6, so it's 18 times 6. The area of this, there we go, the area of this is 108, and it's 108 kips feet. Come on, kips feet. So where does this get to? This gets to 108 kips feet. Am I right in the sloppy? But that's what it works out to be. Now, if you want to do it the other way, we can. I have 108, so if I get to this point, I have 18 times 6, works out to be the exact same thing, right? As I go here, it is this, 18 times 7, minus 20 times 1, right? We start to see these changes. Now, the next part, this area is, again, the change here. So this was the change. I started from 0, I changed by 108. The area of this is going to be negative 2, and the distance is, oh, sorry, 8. Negative 2 times 8. This is a negative 16 kips feet. So 108 minus 16, 92. So this gets to 92 kips feet. And let's think about it. It's going down by 2. So it's doing this for 8. So it's going to be, so it's going down by 2 every 8 feet. So it changes by 16, goes down to this. The next one is 14 times 10. 14 times 10. So this is an area of negative 140 kips feet. Well, it was at 92, and it's going to go down 140. So 92 minus 140, the area is the change. So this gets to negative 48 kips feet. And then I know, I know that I can find the area of this, which is going to be 12. It's going to be 1/2, 12 times 8. 12 times 8 divided by 2. This is an area of 48 kips feet. So it's going to be a positive change of 48. Well, I'm at 48, and I'm going to change by 48, which brings me back to 0. So even without doing all the math we were doing there, we have relationships between these. And those relationships are important. The slope of this line is this value. The area underneath this is the change in this. All right, that is 3 examples of graphing internal forces, graphing the shear force and the bending moment, and seeing the relationships between those two things.